Welcome back to the Engineering Why. Today, we're diving into an explainer that honestly, every senior architect out there needs to hear. Let's kick this off with a bit of a story. Picture this. It's May 1st, 2026. A developer fires up their AI coding agent, a tool called DeepSeek Reasonix, and just lets it run for the entire workday. And by the end of that single day, they had pushed a staggering 435 million tokens through the system.
Section 1. The AI coding cost crisis, and why our API bills keep exploding.
Right, so we all know modern AI agents are incredibly powerful, but they need massive context windows to actually be useful. If an agent can see your whole project, it gets your dependencies, your naming conventions, your architecture, but the trade-off? A huge codebase means a severely bloated context window. Every single token costs money. So if you're making dozens of requests an hour, your engineering team's API bill is going to scale completely out of control.
Exactly, which brings me right back to that insane number, 435 million tokens. As a tech lead, my immediate reaction is, how on earth could a developer afford to push that kind of volume through an agent in one day without literally bankrupting the project?
Well, let's take a look at the receipt because this illustrates the solution beautifully. If you look at standard inference pricing for DeepSeek's top-tier models, that volume of tokens should run you about $61 for that single day of work. That's over $1,000 a month just for one developer. But the actual bill for that specific day? $12. 12. And no, they didn't just switch to a weaker model and sacrifice code quality. They engineered that expected $61 cost all the way down to $12. $12? Okay, come on. I really have to question the underlying mechanics here. The docs for this run claim it was achieved through a 99.82% cache hit rate. How is a nearly 100% cache hit rate technically achievable across that level of sustained volume? Section 2. Prefix caching explained. This is the cost-saving engine. So, to understand how they pull this off, we have to look under the hood. Prefix caching is the core engine driving these massive reductions.
Right. Okay, so I know the textbook definition. Prefix caching is storing the processed representation of the beginning of a prompt to bypass reprocessing identical context on subsequent requests. But if a senior architect is trying to explain this to their engineering team, what's a good practical analogy here?
Think of it like a massive filing cabinet. Imagine you have a human assistant. Without caching, every single time you ask them a question, they have to walk over to the filing cabinet, pull out every relevant folder, read through hundreds of pages of your project's context from page 1, and then give you an answer. That is slow, and it's expensive. But with prefix caching, it's like they just keep those relevant folders open right on their desk. When you ask the next question, they only have to read the new sticky note you just handed them. You replace the high cost of pulling full documents every single time with the cheap efficiency of a desk reference. The context gets processed once, and you reuse it hundreds of times. Okay, that makes total sense. But here's where I've got to play devil's advocate and challenge the design. Why would an architect restrict their entire codebase to this aggressively opinionated DeepSeek-only tool? Why wouldn't we just build this caching logic into a flexible, multi-provider setup so we can hot swap to Claude or GPT-4 whenever we want? Section 3, the 4 pillars of cache stability. It all comes down to byte-stable cache keys. For a cached result to actually be reused, the beginning of your prompt has to be exactly identical to a previously processed prompt. I mean, identical down to the byte level. DeepSeek uses extremely strict byte-stable prefix matching. A generic, use any model you want agent simply cannot be tuned to the hyper-specific, byte-level quirks of one provider's caching system. To get it cheap, you have to be opinionated.
So stability is literally everything here. Can you break down the technical side of how Reasonix maintains that byte-level stability? Because they rely on these 4 pillars, right?
Exactly. These 4 prompt engineering pillars are the secret sauce. First, strict prompt ordering. Your fixed instructions and massive project context always go at the very beginning, and your new specific questions only go at the end. Second, deterministic context construction. The context is assembled byte for byte identically every single time. Third, persistent sessions. It runs as a continuous terminal process, so context compounds over hours. And fourth, this is the big one, deliberately avoiding cache-busting content. Think about typical AI agents. They're constantly injecting variable metadata right into the prompt. Timestamps, request IDs, session tokens. Every time that variable data changes, it instantly busts the cache and completely ruins your cost savings. Reasonix explicitly strips all of that out. Section 4. Fixing DeepSeek failure modes. let's talk reliability. Look, we have to address the elephant in the room. DeepSeek models are fast and cheap, but they have known reliability issues, especially when they're running as autonomous agents making tool calls in a live codebase.
Totally fair. And that is exactly why Reasonix built a dedicated tool call repair pipeline. DeepSeek basically has 3 major failure modes in production. First, dropped tool calls, where the model just completely forgets to use a required tool. Reasonix structurally intercepts this and automatically prompts the model to complete the call. Second, truncated JSON, where it spits out broken or half-finished data. Reasonix catches that and repairs the JSON on the fly. And third, call storms. This is when the model panics and tries to fire off way too many tool calls at once, crashing the workflow. Reasonix automatically jumps in, rate limits, and serializes those requests so things stay stable.
So just to clarify the strategy here, by deliberately shedding support for all those other providers, Reasonix can implement incredibly precise repair strategies. It essentially turns an otherwise unreliable model into a robust, production-ready tool for long-term code-based maintenance.
Section 5. Terminal agents versus IDEs. Let's optimize the workflow. Now, putting my engineering manager hat on, why shouldn't I just tell my team to stick with the standard visual IDE assistants? You know, Cursor, GitHub Copilot, they're already right there in the editor. It completely depends on what you're optimizing for. IDE integrations are fantastic for fast, moment-to-moment edits. You get autocomplete as you type, but you are constantly opening different files and shifting context, which means your cache hit rate is garbage. Terminal-first agents like Reasonix, though, they are built for extended autonomous sessions. You hand it a massive refactoring task, and it grinds through multiple files over hours. In those long sessions, that prefix-cache advantage severely compounds. That is exactly how you hit a 99% cache hit rate and see those massive cost savings. And here's the best part. Just because it lives in the terminal doesn't mean it's isolated. Reasonix adopts the Model Context Protocol, or MCP. It's a really brilliant workaround. It ensures the terminal agent stays flexible enough to seamlessly connect to your databases, your version control, your testing frameworks. You get all the integrated power of a modern codebase without the proprietary lock-in of a specific IDE. Section 6. Real cost and quality trade-offs. When to actually choose Reasonix. Okay, I want the ultimate senior-level verdict here. DeepSeek is great, but we all know it is not the absolute peak of AI reasoning right now. When should an architect genuinely open the wallet and pay for premium models like Claude instead of deploying Reasonix?
It's a crucial question, and Reasonix actually buffers a lot of that need internally with a feature called Smart Model Routing. By default, it uses the much cheaper DeepSeek v4 Flash model for routine, straightforward coding work. But the moment it detects a complex bug or a tough architectural challenge, it automatically escalates to the more expensive v4 Pro model. This smart routing acts as a built-in cost-saving buffer, so you're only burning money on deep reasoning when the task genuinely demands it.
But to answer your question about Claude directly, the trade-off is pretty clear. Premium models like Claude absolutely win for complex, highly intricate architectural reasoning or super ambiguous design problems. If you're designing a complex distributed system from scratch, pay for Claude. But Reasonix vastly dominates sustained, high-volume daily implementation work. Refactoring, writing test suites, incrementally building out features, Reasonix gives you more than adequate quality for a fraction of the cost, making an all-day autonomous agent actually financially sustainable. So synthesizing all this, prefix-cache stability isn't just some quirky optimization for a terminal tool. It's an emerging engineering discipline. It's becoming a mandatory paradigm shift that every single engineering team is going to have to adopt if they want any hope of controlling their API costs at scale. Prompt architecture is basically just cost engineering now. Absolutely. And that brings us to you, the viewers. We really want to hear what you're experiencing on the ground right now. Drop a comment below. What is your current AI coding tool setup? And honestly, what does your monthly AI tool spend look like? Are these costs starting to become a barrier for your engineering team? Let us know. It really is the most important question for the future of your engineering budgets. Are you actively engineering your AI costs, or are you just blindly accepting whatever the API bill says at the end of the month? Something to think about. Thanks for tuning in to this explainer on the engineering why. We'll catch you in the next one.